passado com Schlumberger, depois de 38 anos trabalhar com eles. Eu sou canadense, eu tenho um degree em Electrical Engineering e depois na universidade eu começo com Schlumberger, trabalho nos Estados Unidos, Europa, Meio Oriente, pesquisa em Houston e Ridgefield, Connecticut e Boston, Massachusetts. E mais ou menos 9 anos passados eu cheguei no Rio para trabalhar aqui com nosso centro de pesquisas na Ilha do Fundão, bem perto de Sempes e UFRJ. Quando eu aposentou, eu comecei trabalhando no UFRJ, laboratório de Paulo Couto, com meu amigo e colega Edmilson. Trabalhando lá no laboratório de Advanced Recovery, chamado LRAP em português. É muito bom para mim, todo mundo conhece agora, a pre-salt tem muito petróleo. Mas o problema com reservatórios carbonatos é sempre no recovery factor. Alguns campos no Meio Oriente só têm recovery factor 10%, outros 70%. Provavelmente com o pre-salt, Petrobras vai ficar muito feliz em o recovery factor é 25 ou 30%. Mas com o laboratório de Paulo Couto, a gente espera, a gente pode trabalhar com um recovery factor muito mais alto. Observatório Nacional muito famoso por geophysics. The geophysics é branch of physics também. E como empresa Schlumberger Physics é muito importante também com ferramentas para a perfilagem e sempre physics-based. Eu sempre olhando para novos developments com physics-based measurements, pesquisa e processing também. Espero vocês tenham algumas ideias com minha apresentação today para avançar na physics, com os sensors e com o processing theory também. Aqui você tem timeline on the first electrical log developed in Schlumberger perto de 100 anos passado, relativo para o first oil well nos Estados Unidos. A gente tem oil wells para 1000 anos ou mais na China. Petróleo começa na China 500 anos antes de Cristo. Mas the first modern poço de petróleo foi em Pennsylvania, nos Estados Unidos. Elas usam steam engine para a perfuração. The modern petroleum industry começa mais ou menos aqui. Mas a gente precisa mais 60 anos, 70 anos para a primeira perfilagem. E a ideia para a primeira perfilagem foi com a ideia para geophysics com the surface. The first log is electrical. A segunda chamada spontaneous potential. Mais tarde gamma ray logging, natural gamma ray logging, uranium, thorium, potassium. Muito importante para defining arrays, arenitos e falélios. Depois, the discoveries 1930 of atomic energy in Fermi. The neutron was discovered, I think, 1932. Neutron was found to be very sensitive to hydrogen. The primero neutron log, 1941. Neutrons essentially measure the hydrogen index, so that tells you the porosity of the formation. So this was the first log where you could tell the porosity of the formation. After World War II, a new type of resistivity tool came along, the induction log, and it was based on the same theory developed for mine detection. It was developed by Henri Dahl, who was the chief scientist for Schlumberger at the time. He was working with the French and American governments on new mine detection techniques, and that led to the development of the induction log. 1949, they developed micro-resistivity sensors, which led to the development of what we call dip meters and imaging logs, where you could look at the individual shale and bedding laminations until the dip or mergulio of the formation. Later on in 1957, our company had been collaborating with MIT, who were doing a lot of research into atomic physics at the time, and through that collaboration we came up with what's known as the gamma density, and that is the best log today probably for lithology and porosity of the formations. In the mid-1960s, working with Shell, the first acoustic or sonic log was developed. In 1968, most of the pioneering work with NMR had been done in the 1940s, and that led to the first commercial NMR tool. But it wasn't until the 1990s that modern NMR tools were developed, which was a very big development, important for the pre-salt. In the 1970s, logging while drilling was developed. Logging while drilling means you don't need a logging cable anymore. The logging sensors could be put on the drill pipe, and data could be acquired while you were drilling the wells. So you think about that 120 years after the first oil well drilled with a steam engine, finally they could take measurements while they were actually drilling the well to see what the formations were. Another big development for the pre-salt was what we call gamma spectroscopy or nuclear spectroscopy, developed in the 1980s, where you actually bombard the formation with high energy neutrons, and as they decay, then the gamma rays they give off are an indication of the minerals present in the formation. And this is tremendously helpful in the pre-salt formations, where you have very complex mineralogy. In the 1980s, early 1990s, image logs started to develop much more capabilities in terms of their resolution, and you could actually see the bedding planes, see the vuggy porosity, see the fractures in the formation. Another very important development for the pre-salt. By the 1990s, the quality of the logging while drilling logs advanced so much you could actually now do some sophisticated analysis with the logging while drilling. And today it's used extensively in the pre-salt. 20 years earlier, the logging while drilling was very basic, basically gamma ray and uncompensated resistivity logs. And then in the 1990s, with the development of modern NMR logs, this really enabled advances in the processing and development of logging sensors, and that really helped a lot with the carbonate formations in the pre-salt. So when you do carbonate interpretation, like we have in the pre-salt, we typically split it up into 3 distinct steps. The first step is to understand the lithology and the porosity of the formation. If you're lucky, you might just have one mineral, usually limestone. The most basic carbonate formations are just limestone. And many of the formations in the Middle East are just limestone. But several of them also have dolomite in them. Several of them also have silica or quartz in them. And that's what we have in the pre-salt. We always have a mixture of limestone, dolomite, and quartz or silica. And understanding the percentage of each is critical to coming up with the right porosity. But we also use NMR porosity because the porosity you get from the NMR tool is insensitive to the type of formation. It's merely responding to the hydrogen in the pore space. And water and the oil and the oil-based mud that we typically see in the pre-salt has a hydrogen index of 1. So the NMR porosity with no lithology effects is actually found to be quite often the best porosity in the pre-salt. So once we know the porosity and the lithology, the next problem in carbonates is what type of pore system do you have? Are the pores small? Are they medium? Are they large? And we have different classifications for carbonate pores. The most basic is uses micro, meso, and macro porosity to denote the different pore systems. Petrobras has expanded on this. They include mega porosity and one other one. I think I can't remember the name, but they have 5 porosity types. And so we use NMR to help with that. We use image logs. We use formation testers that can actually determine the permeability of the formation. Usually on the pre-salt wells, there's core data where we can get porosity and permeability. And we're finding sometimes in the pre-salt an acoustic-based permeability based on the Stoney wave can be very helpful as well. Then finally, the last step is where we want to determine how much oil we have. And we also are interested in what we call the wettability of the oil. Is the oil wetting the grains of the formation, or is it the water wetting the grains? Whether it's the oil or water wetting the grains has an impact on the recovery factor and the relative permeability. So these are the important 3 steps for evaluating carbonates. And so I want to look at these 3 steps and all the different sensors in terms of the physics underlying it, what still needs to be done in terms of new sensor development or interpretation and processing. So I'm sure you're familiar with the idea of petroleum reservoir, where you need a seal, the reservoir, some kind of structural trap, and some kind of source rock. And so over 100 years ago, geophysics really played a role in this. Initially, magnetics and gravity coming from the mineral industry, where magnetics would show ore bodies, etc. And gravity in particular was useful for indicating where you might have a salt dome. The contrast in density would show up on the gravity. But the way Schlumberger got started was they started doing surface resistivity surveys. Quite simple in concept. You would have a source voltage here, a sink, and then you would have 2 electrodes here that you could move, and the midpoint of the electrodes you would measure the potential, and you would come up with these lines of equipotential, and often that would show the shape of the underlying ore body, or if it were a salt dome, the underlying salt dome. And then with World War I, in advances in seismics, particularly in artillery, where they tried to determine where the cannon fire was coming from, how far away it was, etc., so they could counterattack. There were big improvements in refractive and later reflective seismology, which were then applied in the oil industry. So just if you look at the technology, the initial magnetometers, the gravimeters, in a way these are still used today in logging, but they're used as auxiliary sensors to orient the tool. The magnetometers to orient us with respect to north, south, etc. The gravimeters now are accelerometers, and they tell us whether the tool is 90 or 80 degrees, etc. So with these sensors today downhole, we can actually orient the measurements very accurately, and that's very important. But the 2 main sensors that went from geophysics to downhole measurements would be electrical and seismic, which in terms of well logging we normally refer to as acoustics or sonic logging. So the 2 Schlumberger brothers, Conrad and Marcel, came from an old French family that made their fortune in the textile industry several centuries before, and Conrad and Marcel, one was an engineer, one was a physicist, and they developed the idea of electrical prospecting for the mining industry. But the Schlumberger family also had interest in an oil field in northern France, and That's where they got the idea of applying these geophysics, in particular electrical measurements, in the oil well itself. In terms of seismic, they went from refraction seismic. Very quickly, reflection seismic took over, because not only could you see the salt domes, anticlines, etc., with the reflections you could also get an idea of the layers, whereas with refraction seismic, all you got an idea was the outline of the shape. You didn't get any idea of the layers like you could with reflection. So here's the very first electrical log run in 1927, and this is very similar to the surface electricity or resistivity measurements, where you had a source, and here's the neutral or ground right here, and then you have the two measurement electrodes, and the spacing between these electrodes tells you your vertical resolution. So if they're close together, you'll get very high resolution. If they're further apart, you'll get worse vertical resolution, but you typically get a reading that is deeper into the formation. And when you think about most oil wells, they're drilled with mud, and the mud would invade into the formation and move any oil or gas away from the wellbore. You have this trade-off. You want to read deeper, so you see the hydrocarbons because they have high resistivity, salt water has low resistivity, but you also want to have good vertical resolution. So with resistivity logs and several other sensors, but particularly with resistivity, you constantly have this trade-off between reading deep and reading high resolution. Now, what they noticed was the first logs, they didn't have a generator, they had a battery. And to save the battery power, they would turn the tool off while they were going in the hole. But the engineers noticed that the galvanometer, or voltmeter right here, would keep reading as they were going down in the hole, even though the battery wasn't connected. At first they just thought that was noise. But they noticed that the tool, if the tool stopped, if it hit a ledge in the wellbore and it couldn't move anymore, then they noticed that the galvanometer, or the meter, would stop reading. And that's how they could tell the tool had stopped, and they would tell the person operating the winch to bring the tool up a little bit and try descending a little more to get past that ledge. That's still a problem today with logging, trying to get the tool to the bottom. You really have to watch the tension and the sensors to see if the tool has stopped moving down. And so they decided to start recording the data when they had the battery off. And what they noticed was that there was quite a lot of consistency when they would compare the peaks on the voltmeter when the battery was turned off between one well and the next. And they called that the SP log, or the spontaneous potential. Sometimes it's called the self potential. And it took quite a long time to understand what was causing that. About 100 years earlier, a German researcher had done some work with electric currents and water, and if he put, say, salt in the water, he could actually make the water move by applying an electric current. And with the same inverse idea, if you had current or water with ions in it moving, you could create an electric current through the motion of the water. And Conrad Schlumberger was aware of that, and so what he thought was happening is when you drill a well, typically the mud in the borehole has higher hydraulic pressure than the formation pressure, and so the mud invades into the borehole, especially the mud filtrate. So the hydraulic pressure is greater than the formation pressure, and that movement of the mud into the formation is giving you this electrokinetic effect. And for quite a few years they assumed that was the cause of the SP, or the self-potential. But when they started working out the theory and putting the numbers together, what they discovered was that the measured voltage in millivolts was way higher than the theory predicted, and that led them to do a little more work. And they discovered two other causes. One is called the membrane potential, where if you have a shale above a sandstone formation with salt water in it, then the difference in salinity will lead to this current flow through the shale here, where you get a complete circuit here. You also get another potential, almost like a capacitance effect here, where you have a zone of one salinity versus another, so you'll have an excess of positive and negative charges near that junction. So this is called the junction effect. This is the strongest effect. It's about 5 times the junction effect. And you rarely see this electrokinetic effect, but I think we see it right here. This is the SP curve in black. In green you have the gamma ray curve. So the SP curve, when it reads here, it's typically an indication of shale, where you have this strong membrane effect from the shale. And then as you get into the sandstone, where you have low gamma ray because there's not much radioactive material compared to shales, you have sandstone here, and then you get back into shale here. Now the black is the SP, and you can see it agrees with the gamma ray till about here, where it deflects further. And often, if the SP is deflecting more than the gamma ray, that's an indication you could have some of this electrokinetic potential, which means the mud is actually invading into the formation in real time. Usually by the time you log the well, this is more or less balanced. You have mud cake built up here, and you don't have this electrokinetic potential. So in terms of the pre-salt, we don't usually get an SP curve. They typically drill with oil-based mud, and when you have oil-based mud, you're not going to get a reliable SP. The other problem with offshore rigs in particular, especially when you're in deep water and you don't have a connection to the sea bottom, so if you're on a drill ship, you'll have no way to complete the full SP circuit to get it to ground, so you typically have a hard time acquiring an SP when you're offshore. So we don't really use the SP in the pre-salt, but there's a couple of things to keep in mind. Because of the relationship with flow, there's the potential to come up with a permeability measurement based on electrokinetics, where you use acoustics to actually get some flow in the formation based on what we call the Stoney wave, where the Stoney wave is actually moving up the borehole on the interface between the borehole and the formation, and it's actually pumping mud filtrate into the formation in and out again. And so that movement is actually used to determine what we call Stoney permeability based on acoustics, but that same movement of water also creates an electrokinetic effect that has been measured in the lab. Nobody has yet built a downhole tool to do it, but I know that the Russians are working on it. So, maybe 10 years from now or something, there actually will be a logging tool to measure the electrokinetic effect and permeability. So this is, in particular, could be of interest with some of the geophysics applications at this institute. The other thing to keep in mind is the pre-salt is undergoing water flooding right now. Lula Field, Sapinyoa, both have water injectors out on the flanks now. And when you inject water into a field, you want to know where it's going. And so that moving water creates an electrokinetic effect as well. And with some experiments we've done on permanent monitoring, we actually can see this electrokinetic effect as an indication of water encroachment. So longer term in the pre-salt, we could see this applied on what we call instrumented wells, where we're actually looking for this electrokinetic effect to indicate that water is on its way to a particular well. And if you know the water is about to come in, then you can take some remedial action in that well. You may have some downhole valves that you can activate to close some perforations, etc., before the water comes in. So this is probably the only pre-salt well that I've seen that is available for the public to look at. This is the Libra Discovery well. It's on the website for the A&P, and that's why I've shown it. So this is the gamma ray curve over here. Are any of you aware of what this is here? One way Petrobras knows they're getting into the pre-salt is they look for what they call Lula's fingers. Any of you aware of that term? Probably Edmilson knows, huh? How many fingers does Lula have? Yeah. So there's actually 9 peaks on the gamma ray there. And I probably went to over 1,000 drill rigs when I was younger. And there were plenty of times I saw people with only 9 fingers on the rigs there too. But this is an indication you're getting into the pre-salt. And right up there is the salt. You can't see it on the log, but typically there's either salt or anhydrite. And then this top formation is called the sag. This formation here is called the rift. And it really comes back to the time in plate tectonics as the Atlantic is opening up. The rift is when there's more geothermal volcanic activity. The sag is when the plates have moved away a little bit and the geothermal effect is reduced, and when the formations cool, they sag down. In terms of elevation, they create more of a basin, and they accommodate a lot more sediment buildup. And here is the partition between what we call microbial carbonates and coquinas. Coquinas are basically small shells. These would be very similar to the type of carbonates you see in the Middle East or as you see above the salt. This is the resistivity log here. So you have fairly low resistivities, and then they rapidly increase because you come to the oil-water contact here. The salt water has lower resistivity. The oil has very high resistivities here. These are the density neutron and sonic logs here. The neutrons in green, the red is the density. The scale on this is minus 15 to 45. So what this is showing is about 15% porosity here, about 10% porosity here, and about 8% porosity here. And I still remember the first time I saw a log from the pre-salt. I've been so used to looking at the formations from the Middle East where the porosity is 25, 30, 35%. And I saw the porosity logs and I said, what's everybody so excited about here? You know, the porosity's, it's okay, but it's not that great compared to the Middle East. But the key to understanding the pre-salt is when you look at the NMR log. This is the NMR porosity here. It agrees with the density neutron. But the real important information is in what we call these T2 distributions, which are a proxy for the size of the pores. So the bigger the pores, the further out to the right the T2 distributions. And this is something that Giovanni is actively engaged in here. Sylvia, you work with NMR too, and carbonates. So this is a very nice connection because some of the early lab measurements we did to understand the pre-salt cores were done here with Edmilson in the labs here at Observatory National. When I just looked at the density neutron logs, I was a little concerned, but when I saw the NMR logs shortly after, then I really understood why the pre-salt is such a big deal. And so you see here, this is 5,400 meters, 5,700 meters. That's about 1,000 meters of oil. So this particular well here is probably, could make up to like $10 billion in its lifetime. And it probably cost maybe $100 million to drill. So you can see why so many of the big oil majors want to be involved in the pre-salt. There's really nowhere else in the world will you find this kind of reservoir right now. And so if you remember the original resistivity log, it has evolved now with what we call ladder logs, where we actually have current injection, and then we have different sensors with different spacing to try to focus the measurements and get higher resolution and also read deeper into the formation. So this has evolved almost every 10 years. There's been an improvement with what we call ladder logs. And these work fine when the drilling mud is water-based, whether it's high salinity or low salinity. It works best when it's high salinity. But in the 1950s, oil companies started drilling their wells with oil-based mud. They found that drilled faster, they had less problems in the shales. The shales wouldn't swell up due to the high water content. And ladder log type resistivities won't work in oil-based mud. And that's what led to the development of the induction log, originally based on mine detection concept, where you had a transmitter that was typically had a current at about 20 kilohertz, and that would set up a ground loop in the formation that would set up a secondary current on a receiver coil here, and the strength or the amperage or voltage on this receiver coil was a direct function of the current flow here in this current loop, which reflected the resistivity of the formation. So even today, we still use both sensors in the pre-salt. They're moving away from oil-based mud because oil-based mud is quite expensive. It's a lot cheaper to use salt-based mud. And so now we're going back to ladder logs in the pre-salt, but still we do see a lot of induction logs. So in terms of the evolution of induction logging technology, it went from a single array in the 1950s to 2 arrays, where one was deeper, one was shallower. That eventually led to multi-frequency arrays, where you could play with the fact that the higher frequencies didn't propagate as deep, so you could look shallower in the formation based on frequency. But eventually it led to multi-arrays, where most of the what we call subtraction is done. So if you want to isolate one particular depth in the formation, you can actually use computer processing now to subtract out the effect of other arrays to isolate certain depths of investigation. And so this works very well. Now in the 1990s, a company called EMI, based in outside of San Francisco in California, developed what we call cross-well induction technology. So you would have one well where you would have a transmitter, and another well you would have a receiver. And that allowed you to image between the two wells. And there was a lot of interest in using this technology to look at water flood advancement in particular, because the water is lower resistivity. So we tried this for several years in the Middle East, and it does work. You can see the water flood coming, but there's logistics problems with accessing 2 wells at the same time, being able to do that. And eventually, companies like Aramco, etc., they felt they could see the flood, but they couldn't really tell enough about the shape of it. Was it convex? Was it concave, etc.? They wanted to know this additional information, because that told them extra information about the wettability and recovery factor of the formations you're sweeping. So this is not used near as much as we hoped it would be, mostly because the resolution and the logistics of getting access to do 2 boreholes at the same time. By the late 90s, early 2000s, though, we moved to what we call triaxial inductions, where you not only have a current ring in this direction, but you can have one in this direction and then in this direction. And this is a big advance, especially for above the salt in the turbidite formations, where you have layers of sand and shale. But also it's quite helpful in the pre-salt as well. And this is a schematic of the newest tool, where you have these additional triaxial receivers to give you information, not just from current flowing in this direction, but from current flowing in this direction and current flowing in this direction as well. Now, we occasionally use this in the pre-salt, because in the pre-salt you can sometimes have what we call laminated formations. And here's an example of a laminated formation where you have a shale with thin layers of sand in between. And if you went with the older style induction log, where you had this shale sand, and if the sand had hydrocarbons in it, the hydrocarbons would make the resistivity read high. But because the current is flowing in this direction, you're essentially just measuring the shale resistivity. The overall effect is a resistivity curve like this. And we're not really measuring the true horizontal resistivity in these thin sand layers that are filled with oil when we have a single induction log like this. But if we go to a triaxial one, you will see this is the horizontal resistivity, and these are the vertical resistivities here, out here, because they're responding to those oil-filled sand layers. And we do see this type of situation occasionally in the pre-salt. They're in carbonates that are called lamanites, where you have these sequences of muddy carbonate shale with some higher porosity carbonate that could have oil in it. So this is useful in some parts of the pre-salt. But one problem we have still today is you might have a high porosity formation filled with oil, but you could also have a low porosity formation that's not very permeable that'll give you high resistivity. And so using this technique is still difficult to tell whether you have thin beds with oil or if you just have thin beds that are low porosity and high resistivity. And these beds are so thin you can't resolve them with other logs to evaluate their porosity. So what we're looking at now is actually rock physics modeling. And some of you may be familiar with rock physics modeling in laminated formations, where you have different effects. Usually in formations with porosity, you'll have pores that have an aspect ratio of somewhere between 1, which would be a sphere, maybe 3, which would be an ellipse, compared with the shale, where you have very high aspect ratios associated with the very platy grains you find in the shale. And that has a big impact on the acoustic rock physics. So what we're working on is different rock physics modeling, where you can essentially keep the shale, but you can vary things like the aspect ratio and the porosity in the sand to go from a porous to a non-porous situation. And then you can look at the effect and look at this rock physics for laminated formations to see if you actually have porosity between the shales or if you actually have tight formations. So this is something that still needs a lot of work, but it could be of interest to some of you working in terms of geophysics of anisotropic formations here. If we go back to the first porosity log, the neutron log that measures the hydrogen index, it's essentially still the same idea today. Today we generally use a chemical source for emitting these fast neutrons. Then they collide with the hydrogen protons. They slow down, they emit gamma rays. The gamma rays are captured with a scintillation detector here. And the energy level of the gamma rays can also tell you some information about the formation. But basically the response to the hydrogen protons tells us what the hydrogen index of the formation is. And in the pre-salt, some of the fields have very high CO2 content. So if you have high CO2 content, that will lower your hydrogen index because the CO2 doesn't have hydrogen in it. So we're particularly interested in using the neutron logs today to see if we can see changes in the CO2 content of the oil. In particular, we like to compare the logging while drilling neutron log with the wireline neutron log. The logging while drilling neutron log will see more of the native oil, whereas the wireline logs, they've been acquired typically a few days to a few weeks after the LWD logs. So you get more oil-based mud filtrate invasion, and that oil-based mud filtrate has a hydrogen index of above 1. So any contrast you see between logging while drilling neutron logs and wireline logs could be an indication that you've flushed some of the CO2 from the formation. Density logging, most parts of the world, this is the most reliable log for getting porosity. But to understand the porosity, you need to understand the mineralogy. Limestone has a bulk density of 2.71, sandstone 2.65, and dolomite 2.85. So to determine the porosity of the formation, you need to know what the effective bulk density of the formation is. And because the pre-salt is a mixture of these three, it can be difficult to determine the porosity exactly just from the density log. Now we have a second measurement with the density log based on the photoelectric effect, which is a different mechanism. So with the density log, we emit high energy gamma rays, and there are two types of interaction. One is called Compton scattering, which is sensitive to the electron density of the minerals, and the electron density is directionally proportional to the bulk density of the formation. And then we have the photoelectric effect, which is lower energy interaction. And the photoelectric effect tells us the photoelectric cross-section of the formation, which is another indication of the mineralogy. So using this, we can get a better understanding of how much limestone, sandstone, and dolomite we have, and then we can actually determine the porosity better because we can determine what the effective bulk density is of the formation. In terms of future direction, a lot of work being done now and actually over the last 20 to 30 years on coming up with a gamma source that is not chemical based. And actually, in terms of logging while drilling tools, we actually have a tool called the Neoscope that has a neutron source, and there's enough gamma-gamma activity from that source that we can actually come up with a reasonably good density value. We don't have that yet available on wireline tools, but eventually we see that coming. Now, one of the interesting things we see in the pre-salt is we see what we call karsted formations, which are essentially big caves downhole, very high porosity, and they can be a few feet thick, sometimes they can be 10, maybe 20 feet thick. And when you see these karsted formations, often the wireline tools won't work that well because you don't have good contact with the borehole wall in these highly karsted formations. So we have a difficult time evaluating what is the true porosity in these karsted intervals. So one potential measurement here would be go back to gravity sensors. With the technology available today, we're probably at least a factor of 10 off in terms of the accuracy needed to do that. But maybe there'll be some improvements in the accelerometers, etc. Or we can actually leave some of the accelerometers in the borehole, maybe cement them behind casing so that they can stay there permanently, and we can get, by stacking the data long enough, we could get an accurate gravity measurement that we could then use to determine the bulk density of the formation near these karsted intervals. So, not sure when this will happen, but if gravity sensors ever get accurate enough, we can use them for continuous wireline logging. I think you'll see a lot of interest in the pre-salt. Gamma spectroscopy or nuclear spectroscopy has been a very good development for the pre-salt. With gamma spectroscopy, we basically have a pulse neutron generator emitting very high energy neutrons, about 14 to 15 keV. And the neutrons interact with the formation. There's both inelastic and elastic interactions. And then the gamma ray and the energy level of the gamma rays given off can be measured, and that tells us the amount of magnesium, silica, calcium, sulfur, hydrogen, etc. And what we have here is a comparison of the newest detector technology, lanthanum bromide, versus the older bismuth germanium detectors. So this is at room temperature, and the new technologies in blue, the older technologies in orange or red. And you see, they're reasonably close to each other. But the older technology was very poor when you had higher temperatures. This is at 60 degrees C. Most of the pre-salt wells are somewhere between 50 and 60 degrees C. So tremendous degradation with the older detectors. Whereas the newer lanthanum bromide detectors are still very high resolution. And this is at a very high temperature here, 150. So big leap forward in terms of detector technology over the last 10 years or so has led to much wider use of gamma spectroscopy, and it's used quite a bit now in the pre-salt. As you can see, here's the inelastic energy release here in terms of the inelastic gamma rays. Here the neutron is captured and you get capture gamma rays. So different energy levels, and based on these peaks, we're actually resolving the spectra in terms of these minerals. We actually saw for 20 different minerals. Now this works quite well for the important minerals. Silica tells us how much quartz or chert we have. Calcium tells us how much limestone. Iron tells us what we have in terms of shale. Also heavy minerals. Heavy minerals are a big problem in the pre-salt. Siderite, pyrite, hematite. These are iron-rich minerals, and it only takes a small amount of these iron-rich minerals to have an effect on the density and even the neutron logs. And that is one reason why Petrobras in particular really like to use the NMR logs as a porosity indicator, because even when you have, say, less than 5% of these heavy minerals, it can have an effect on the density neutron log. So sulfur, that tells us how much anhydrite and how much chloride we would have. Chloride has a lot of sulfur in it. Aluminum, very good for the shales. Potassium is particularly good for any volcanics, and from time to time we do see volcanics in the pre-salt. Sodium, very good for feldspars. Often you'll get sodium feldspars associated with volcanics as well. Manganese, titanium, gadolinium, they're also good indicators of heavy minerals. And with carbon, we also get an oxygen yield as well. So using carbon and oxygen, we can have another indication of hydrocarbons. And using this to indicate hydrocarbons combined with resistivity to indicate hydrocarbons could be a useful way to also identify where you have CO2, because you should get an imbalance between the hydrocarbons based on carbon-oxygen versus the hydrocarbons based on resistivity. Now acoustics, not used extensively for formation evaluation in the pre-salt. Acoustics is normally run in particular to help tie into the seismic data. But we're using it more and more to help with the formation evaluation. With acoustics, there are three modes that we're interested in. The P wave, or the compressional wave, which is most useful for indicating porosity and also for tying into the seismic data. The shear wave, also helpful for tying into seismic if you have good shear wave seismic, but is very, very good for indicating fractures as well. If a shear wave hits a fracture, it will split into two. One shear wave will go parallel to the fracture, that's the fast shear wave. You'll have another shear wave that's propagating 90 degrees to the fracture strike. That's the slow shear wave. So we look for shear wave anisotropy as an indication of fractures. Not all pre-salt wells are fractured. Maybe 1 in 10, 2 in 10 have significant fractures. But when they do have fractures, it can have a big impact on the productivity. And then the third mode that we look at is the Stoney wave, which comes later in time. And that's the wave that I mentioned earlier would also create an electrokinetic effect, because it's actually moving the fluid in and out of the formation as it moves up the wellbore. So the older sonic tools were very simple. You had one transmitter and two receivers here, another transmitter, and you would actually use very simple interferometry to come up with the travel times. The newer tools actually use semblance processing. The latest tool actually has 13 receivers, so you can do semblance type processing over that entire receiver array to get the velocity and the slowness in terms of the move out, just like you would for seismic processing. And by using semblance processing, you can solve for the compressional arrival, both the fast and the slow shear, and also the Stoney wave. So here's some results of some shear anisotropy in a fractured interval. So this is an image log, and you can see these fractures right here. This is the fast shear, this is the semblance plot. Red is high semblance, so you're getting very good cross correlation here. This is slowness on this axis. And this is the slow shear here. And what you find when you have the fracture, you get a difference between the fast and the slow shear. This is the frequency of that flexural shear wave. This is low frequency here, this is high frequency here. The low frequency waves go deeper into the formation, the higher frequency waves stay on the side of the wellbore. And when you have stress or fractures, you get different response. If you have fractures, you see this parallel effect between the slow and the fast shear. So this is typically what you like to see when you're looking for fractures here. And as the shear wave strikes the fracture and creates the fast and slow shear wave, you also get what we call this offline energy, 90 degrees to the incident shear wave. And where you have fractures, you see this increase in offline energy. And what you have here is an indication of fractures seen by the Stoney wave based on reflections. When the Stoney wave sees a fracture, it pumps the water into the fracture and also sends a reflection back. So we can look at both the slowdown in the Stoney wave and the reflections as an indication of fractures. So you can see, we see these fractures right here. This is a cartoon of the data. This is the actual data. Red is the fast shear, blue is the slow shear. You can see that this parallel effect. Now when you have shear anisotropy due to stress, and you have quite a bit of stress in the pre-salt because of the fault blocks associated with it. Some of the wells, we think the lateral downhole stress is actually higher than the overburden. And up here, we don't really have any clear fractures on the image log, but we have some indications of drilling-induced fractures, and we also have shear anisotropy up here, but we have this crossover effect. You can see a little bit of the crossover effect. It's subtle, but on the log data you can actually see it. And this is because of the hoop stress effect. if you've got uneven downhole stress, it gets magnified due to the hoop stresses at the wellbore, and then it decays as you go away into the far field. So near wellbore, the stress direction is 90 degrees different from the far field, and that 90 degrees difference leads to this crossover effect. So near the wellbore, you get the fast shear here, but as you move further, the far field, the low frequency, you see the true fast and slow shear. But as you start to feel the hoop stresses and get near the wellbore, you get this reversal in the fast and slow. So we use this in the pre-salt to better understand what are natural versus what are drilling-induced fractures. And the next step is, if we combine this idea where it's called four-component rotation, where you rotate the fast and slow shear to get the ideal orientation of the true fast and the true slow, you can do the same thing with the 3D resistivity tool, and that's what we've done here. And with the resistivity tool, we start out with, I think this is about a 15-inch, and then we're moving to 20 inches, 25, 30. Finally, we get to about 50 inches deep into the formation. And what this is here is basically the difference between the inline and the offline rotated resistivities. So the inline resistivity is now aligned with the fractures, and the fractures are filling up with the oil-based mud drilling the oil-based mud filtrate, which is high resistivity. So this difference in resistivity, and you can see it's consistent as you go deeper into the formation. This is an indication these would be natural fractures. So this is a big step forward in terms of multi-physics and geophysics for pre-salt evaluation, where you look at anisotropy in terms of electrical and acoustic terms to try to resolve these shallow drilling-induced fractures from the deeper natural fractures. The deeper natural fractures will have a big impact on production, but they'll also have a potentially big impact once you start water injection. If you get water injected into these fractured networks, you can get water breakthrough extremely quickly and make the well maybe uneconomic. So it's very important to map these fracture corridors, and this is a big step forward in terms of both the sensors from a physics perspective, but also the processing as well. What we have here is in the dots, these are this is the orientation of the fractures as we see on the image log, and then the shaded area is the orientation of the fast shear based on the four-component rotation. And where you see good agreement is usually where you have these natural fractures. Where you don't have the fractures, you get this ambiguity. You don't have really much signal in terms of fast and slow shear to really resolve the angle of the downhole stress or the fractures. So you'll often get disagreement here. And then over here, this is the difference between the offline and inline energy that occurs when the shear wave splits. So here you have good difference. Down here, because there's no fractures, very little stress, you don't get any shear wave splitting. Step is to look at the acoustics more in terms of seismic type processing, to look for these deeper reflections coming from the natural fractures. And this is still got a long way to go in terms of being done routinely. It's very time consuming in terms of the processing, and that's one reason it's not extensively done today. But this is potentially something that could be improved using artificial intelligence, etc., supercomputing, to really speed up the processing time in terms of evaluating basically acoustic logs with seismic type processing to really image beyond the wellbore. So we were talking about images and acoustic and electrical response, and images are also helpful for looking at the types of carbonates. So remember that log we looked at earlier, we said there was one zone with coquinas. Here is an image log in a zone where you have coquinas. So the dark spots, they're an indication of this vuggy porosity. The dark spots are indications of low resistivity or higher conductivity. And what you'll typically see on the image logs is these will exaggerate the effect of the vugs. These vugs look very big, but often when you actually look at the cores, they're quite a bit smaller. And the reason is the current from the sensors are 5 millimeters in diameter. The current basically sinks in to these small vugs, and they appear magnified on the image log. So the image log shows you where the vugs are. It's not so good in terms of quantifying the porosity of the vugs based on the image, but very good to show you where they are. So this is an image of coquinas, and Petrobras, other companies, Schlumberger as well, they're working with their geologists who look at these images every day. And ideally, you can see, with all the work being done in terms of facial recognition, all the controversy involved with that, you would have facial or image recognition techniques to indicate where you have coquinas. We're not there yet, but a lot of people are working on that type of stuff. The pre-salt's famous for its microbial-like carbonates, stromatolites in particular. This is a stromatolite. Typically they grow in very hypersaline lagoons, and you get this arch effect. And you can see that on the image logs. So if you go back to that previous slide, the contrast between this and the coquinas, a good geologist could probably tell based on the images. Oh, here we're in the coquinas, here we're in the stromatolites. It may be a bit of a stretch for many of us to say that, but people who look at these image logs every day get quite comfortable doing this. This also brings up another point. You can see with this arch, you actually have a built-in mechanism to help preserve porosity. An arch can withstand a great deal more overburden than flat beds could. One of the amazing things about the pre-salt is the porosity preservation. It's quite deep, and typically for a formation that deep anywhere else in the world, you'd probably expect to see about 5 to 6% porosity because so much overburden will compact it. But when you have these arches, they help withstand that overburden and preserve the porosity. There's another important effect in the pre-salt too, with the faults and the hot salt water coming up. It can actually dissolve the pore space or dissolve the calcite grains and enhance the porosity. So you get two effects. You get this arch effect helping to preserve the porosity, and you also get this acidic water that can actually increase the porosity in some zones, but eventually that water becomes calcite rich, and as it moves away and cools down, it will actually precipitate that calcite, and you will lose porosity in some areas. So most of these pre-salt wells that have not produced oil have been because you've had precipitation of other minerals as the hot hydrothermal fluids move away, they cool down, and you lose porosity. So there you're losing porosity due to precipitation, not so much compaction from the overburden. Now, in addition to the coquinas and the microbialites, there's pretty strong indications now that there's travertine deposits in the pre-salt. Travertine is normally associated with hot springs where you essentially have calcium precipitated, and you get these vuggy intervals. Very good reservoir. They're not common in terms of oil field reservoirs, But more and more you're seeing indications that travertine buildup can be quite important in some of these pre-salt fields. So I don't have an image log in the travertine, but as soon as I get one, I'd be quite curious to see, can you distinguish travertine from coquinas, and also from the stromatolites. So we're going to finish up now talking about magnetic resonance. It's one of the newest logging technologies, and it really became mature just in time for the pre-salt development. The first logs developed back in the 1960s. You actually had to treat the mud with iron particles to kill the magnetic resonance signal from the mud. With the newer tools, you don't have to do that. The newer tools came out in the 1990s, and they really led to widespread adoption of the NMR. And so with NMR, you essentially have a fixed magnet to actually polarize the formation, and then you have an electrode magnet to actually pulse the formation, cause those polarized hydrogen protons to precess, and then we measure the precession, because the precession is an indication of how quickly they interact with the grains in the formation and give us an idea of the pore size. And so the pre-salt is particularly good for NMR. With the 2 kilometers of salt overlaying the carbonates, the salt basically acts as a big chimney to allow the heat building up in the earth to escape. So the pre-salt formations, for their depth, are not very high temperature. NMR doesn't work as well at high temperatures because of the Brownian motion affecting the hydrogen protons. So lower temperatures are good for NMR. The pre-salt, for its depth, is quite low temperature. The low temperature also helps preserve the oil. Higher temperatures will degrade the oil. The pre-salt has very good quality oil. Doesn't have very high gas content. And what that means is its hydrogen index is close to 1. With a hydrogen index close to 1, we can use the NMR because the NMR is essentially responding to the hydrogen index. So it's very good for porosity. So here's an example of one of those stromatolites from a core. You can see here, probably got some quartz or chert. You can see the vuggy porosity here. This is a mixture of calcite, dolomite quartz, plus heavy minerals. So because the NMR porosity is insensitive to the minerals, it's very good. But we have tremendous permeability range, about 4 decades, from about less than 1 millidarcy to a darcy or more. When you get these tremendous flow rates, that's an indication you have permeability in the darcy range. Another feature about the pre-salt is it's oil wet, typically, which means the oil is actually in contact with the grains. And that also helps us in terms of the NMR response. So with the oil wet properties, we also get very high resistivity because there's not much water to lower the resistivity. This makes it hard to determine the water saturation based on resistivity itself. So we can also use the NMR to help determine the water saturation of the formation or the oil content. So here's an example of an NMR T2 distribution. This is an indication of larger pores, medium pores, small pores. In the small pores, this is where the capillary bound water resides. And the larger pores, that's what gives us the Darcy quality permeability, the very high flow rates. But you still have tremendous reserves here in these lower perm intervals. So the big goal for the pre-salt will be to not only produce the oil from these intervals, but also to produce the oil from these intervals before the water breaks through from the water injection. So this is how NMR behaves in terms of the main 3 components that make up the NMR response. Surface relaxation is the one we're most interested in, where the hydrogen protons start to precess after they're polarized, and when they precess, they'll come in contact with the grain surface, and this gives us an indication of the size of the pores. Bulk relaxation happens when the pores are so large it takes a long time to get to the grain surface. In a case like this, we get an understanding of the viscosity of the fluid. So in the very large pores, we can get an idea of whether we have heavy oil or light oil. In formations where we have a lot of paramagnetic material and we have quite a bit of variation in the magnetic field, we can actually get a strong diffusion effect that can lead to the hydrogen protons decaying very quickly. This is typically not a factor in the pre-salt, but it's something we're looking at in terms of research where we can apply a strong magnetic field to create diffusion, and then we can look at the diffusion in terms of how quickly the hydrogen protons can move from one pore to another, which is another way to get indications of permeability. So, as I mentioned earlier, the bulk effect is a function of the viscosity of the fluid. So if we do look at the bulk effect and we have light oils, we'll get fairly long T2s. And in the pre-salt, we're usually out in this range here. In the post-salt, where we have heavier oils, we're usually down more in this range. And when you're in this range, this means it's harder to use the NMR response to indicate the formation properties. It's really just responding to the fluid. But when you're out here, and if the oil is wetting the grains, then you get indications about the formation properties. And so if we get indications about the formation properties, now we can move to what carbonate geologists like to do in terms of quantifying carbonates. They either look at the grain size, they either look at the pore size, or they look at the pore throat size. These are the three common techniques geologists and reservoir engineers will use to describe carbonates. Usually larger grains means larger pores, higher permeability. Archie, the famous Shell petrophysicist, came up with a carbonate classification scheme back in the 1950s. It's still used to this day by Shell, and it's based on the size of the grains. Jerry Lucia, another famous Shell petrophysicist, now with the Bureau of Economic Geology in Texas and Texas, University of Texas. You've met Jerry Lucia, haven't you? No. He came up with another famous classification scheme. And these other researchers did it based on pore size, looking at the thin sections. And the classification scheme based on throat size use mercury microporosimetry. So all these three systems are actually related, and with NMR we can typically try to get the pore size based on this equation here. T2, which is the decay time from NMR, is a function of the bulk fluid decay time. And if you have very light oils, this is a large value, so you can almost ignore this term. And then it's a function of the pore radius and this constant, which is a function of the surface to volume ratio. So if you have spherical pores, your surface to volume is 3 over the radius. Cylindrical pores, 2 over the radius. And planar pores would be 1 over the radius. So if we know this value rho, also called surface relaxivity, we can relate the pore radius to the T2. And so this is the basis for using NMR for classifying carbonates. And here you have an NMR T2 distribution. This is time in milliseconds on this axis. And this is mercury porosimetry. Oh, sorry, this is mercury porosimetry here, where you have pore radius in microns. And this is NMR, where you have the T2 relaxation in milliseconds here. And so you typically see this correspondence between the peaks on the mercury porosimetry and the NMR T2 distribution. And you can do this cross correlation between the two and come up with this rho factor. And typically in the carbonates, the pre-salt, we typically come up with a rho of about 10 microns per second to relate the radius to T2. And that value works quite well. Now, lately, we've been using a lot of micro CT scans as well to look at images, and the blue is the blue epoxy that's in the thin section. So the blue indicates pore space. Anything that's white or dark is grains. So we can use image analysis to come up with a pore size distribution here. And now what we're doing is comparing those pore size distributions to the NMR. And what we're finding in the pre-salt is this gives us pore size, this gives us throat size, and this allows us now is to get an understanding between the pore throat and the pore body. In sandstones, usually that ratio is about 3 to 1. But in carbonates, we're finding it can get as low as 3 to 1, but more often it's something like 10 to 1, and can easily get up as high as 20 to 1 or higher. And when you get these higher body to throat ratios, that has a big impact on the permeability. It'll also have a big impact on the oil recovery. If you've got big pores and small throats, the oil will snap off and stay in those pores, and the water will come through. So this is something we're going to be looking at quite a bit at Paulo Couto's lab in terms of the effect of body to throat ratio on recovery. So MICP gives us this, NMR gives us this, and the thin section analysis will give us this. So these three ways of looking at the cores we feel are going to give us a nice understanding of this factor rho to correlate the throats with NMR, and also give us a way to correlate the throats back to the thin section analysis. So to be successful doing this with NMR, there's certain criteria you need to have. First of all, you don't want to worry about diffusion, letting the hydrogen protons go from one pore into another. You might want to do that if you're trying to use advanced NMR to evaluate permeability, but if you're trying to evaluate the pore size, you don't want that. You also want to make sure that the fluids have a very high T2 bulk effect, which means you have light oils or you have water in there. You also want to ensure that the pores aren't so close to each other that the hydrogen protons go from one into another. So this is similar to this effect here. And you also want to ensure that the fluids are wetting the grains so they're sensitive to the surface effect. And in the pre-salt, we typically have water in the small pores and oil or oil-based mud in the larger pores. And so when we say wettability, this would be a water wet case. This is neutral wet, and this is oil wet. So if you have oil on top of water and you put a capillary tube in, and your capillary tube is water wet, you get this type of contact angle. If it's neutral wet, you get a contact angle of 90 degrees. If it's oil wet, you get this contact angle of much more than 90 degrees. So with the pre-salt, we're somewhere between neutral wet and oil wet. But of course, the small pores, who only have water in them, they stay water wet. So you get this combination. And so if you look at this equation here, and you plot T2 here versus pore radius here for different fluids where you have a bulk relaxation of 1, 2, or 3 seconds, you see this nice relationship between T2 and radius. But when you get into the very bigger pores, it starts to get nonlinear because this effect comes in, the bulk effect. So when your bulk is higher at 3 seconds, the effect is less. When the bulk is lower at 1, you get a stronger nonlinear effect. So for the pre-salt, we're probably more up around here. So we still get sensitivity in terms of T2 to the larger pores, but it's not linear like here. And the impact of this means that to try to calculate a permeability just based on the logarithmic mean, where it's considered a proxy for pore radius, you start to lose sensitivity when you get into longer T2s up here. So this was a big problem that Petrobras found initially when they started running NMR logs in the pre-salt. They couldn't rely on the permeability from the NMR logs. It would work on one well, it wouldn't work so well on another well, and this led to developing another way to come up with permeability. And another way to do permeability is to actually look at the volume of the larger pores over the volume of the smaller pores. This is known as the Coates-Tamur equation here. This one is known as the Schlumberger-Dahl research equation, SDR, because that's where it was developed. And they're both quite similar in terms of you have porosity raised to an exponent, and then you have some kind of information regarding the size of the pores. Here it's the average pore size. Here it's the ratio of the large pores over the small pores. And when you use this approach, what you find is as long as you're in this interval here, where you're about 20 to 30% larger pores compared to the overall porosity, you get this linear relationship between permeability and this ratio right here. Where you get to the ends, it starts to get nonlinear. So working with Petrobras, we came up with a way to combine this equation and this equation once the macro porosity exceeds a certain amount. And that is the key to understanding permeability with NMR in the pre-salt formation. So some of the work we did, this is Paulo, actually he studied here, didn't he? Yes. Giovanni. This is him at the lab over at Sempes, measuring the bulk oil T2. Here you can see it's about 2 seconds. And this is at downhole temperature. And then we took one of the cores from the pre-salt. First we filled it with brine, and you see this type of T2 distribution. And then we took that oil and centrifuged it in, and the T2 distribution looks like this. So down here in the small pores where we still have water, there's really no change. But in the larger pores where the oil-based mud filtrate has displaced the water, you see this big increase in the peak of the T2 distribution going from here out to here. That's typically a factor of 3. Does anyone know why that happens? It's because the oil molecules are bigger than water molecules. So the hydrogen protons on average are farther away from the grain surface. So that surface relaxivity effect is reduced when you have oil. So as long as you know that, then you can account for it in the permeability equation. Now, if it were water wet and the oil-based mud filtrate weren't in contact with the grains, it would still be out here. So this is an indication that the oil-based mud filtrate is wetting the grains, and we can use NMR to come up with pore size information. And then the next step is to compare the lab measurements on the core to the log measurements. So this is log data from that same depth where the core was taken. This is the core in the lab with the oil-based mud filtrate in it at downhole temperature. You see this a good agreement. This is the oil-based mud at downhole temperature, the oil-based mud filtrate. So we see that downhole we are oil wet, in the lab we are oil wet. So we get good agreement between the lab, good agreement between the log, and this leads to improved understanding. So we still need to know what the surface relaxivity is, and that value rho. And we've actually developed a new way to do this in the lab, and in theory it can be done downhole. And what we do is what we call two-dimensional NMR, where we look at T2, but we also look at diffusion. Remember earlier we had three mechanisms for NMR. We had diffusion, we had bulk, and we had surface. So T2 here is mostly a function of the surface effect. But when we look at diffusion, now we can look at the hydrogen protons as they go from one pore to another, get a better understanding of the surface relaxivity. And so what we do is we look at this 2D data, and we basically come up with the mean value as we go through that 2D data. And the way that traces is a function of rho, and it's also a function of the tortuosity of the formation. And we can actually get the tortuosity of the formation with dielectric measurements on cores, and we can also do that downhole now with dielectric tools. So eventually we feel that we'll be able to come up with this value of rho using downhole measurements. We still can't do it today. The signal to noise is not good enough. This is Andre Souza and William, one of the Petrobras researchers up at Harvard, where they were working with Dave Weitz at Harvard and some of the Schlumberger researchers just down the street to develop this technique. So I hope one day we'll be doing this routinely in the pre-salt. But just to wrap up, still a lot of challenges in terms of sensor development and processing. The SP, even though we don't use it today, there's definitely potential for it in terms of permeability.